Okay, so let's start our lecture today. Uh, so yeah, so we will focus on the calculating the one number, right? So yeah, I feel like this is not the right way to compute the one number. So uh, so yeah, so what I do is that so yeah, so therefore I did some search on the one numbers. So let's see what the search gave me. So uh, okay, so okay, so let's do this. So okay, so let's do this. Oh shoot. Okay, so okay, so let's see. So So our goal is to show that okay, so that zeta naught be the lattice point union 0 be the unique point, unique lattice point inside the parallelogram. So we claim that the Wannier number of boundary PA of zeta naught is equal to 1. Okay, so by definition, right? So for this Wannier number, so by definition, this Wannier number of PA zeta naught is equal to 1/2 pi I of the integral boundary P alpha PA dz over z minus zeta naught. Okay. So okay, so here it says that geometrically as z travels once around the boundary of the parallelogram. The vector z minus lambda, sorry, I use zeta naught, turns once counterclockwise around 0. Okay, so therefore its argument increases by 2 pi. Okay. So 1/2 pi I of the integral over the boundary of PA dz over z minus zeta naught is equal to 1/2 pi delta boundary PA, the argument of z minus lambda zeta naught is equal to 1. Okay, so let's see why is it true. So yeah, so I'm just copying from the ChatGPT answer, but I'm not sure whether it's correct or not. So yeah, maybe it's not correct. Let me see. So yeah, so here we integrate over the boundary of PA, right? So here basically I'm dividing this yeah, I'm not sure why this why integrating over the boundary of the parallelogram is the it's the same thing as just the change of the argument of this vector. Yeah. So let's see. So why? Yeah. So the question is that why integrating over the boundary of the parallelogram is the same thing as yeah, so why integrating 1/z minus zeta naught over the boundary of PA is the same thing as integrating counting the change of angles. I mean, it's not the same thing, right? Because here, there is a left of this I here, right? So there are difference of I. So maybe I use the quote unquote same thing as counting the change of angles of the denominator, right? Right. So why this is true? Right. So why is it true? So you are integrating over the parallelogram, and then yeah, so you are integrating over the parallelogram. So what does integrating over the parallelogram means? So integrating over the parallelogram means that yeah, it's like the line integral, right? So basically, it's like you have the function's values on the boundary of the parallelogram is like the 1 over z minus zeta naught, right? And then you're integrating over the curve. Okay, so it's like you plug in values. Yeah, you just yeah, it's just like the usual integration on like a curve on this curve of these functions 1 over z minus zeta naught. So, and then on the other hand, yeah, I'm not sure why. I'm not sure why they are the same. So, okay, maybe I'll ask this again. Okay, so can you explain to me why? So on the one hand, we have the integral from 1 over 2 pi I, integral over the boundary of the parallelogram of dz over z minus zeta naught. And I'm not sure y is equal to 1 over 2 pi I integrate, counting the total change of the argument. I'm not sure why they are the same thing. Because on the one hand, you have the line integral over the function 1 over z minus zeta naught, right? I think there is a radius. Yeah, so I think there is 1 over the radius, and then I think there is also like the boundary integral right? So the boundary line integral be in play. You have to kind of sort of counting the boundaries, right? So, and on the other hand, you also want to count the 1 over the distance, sort of the the difference between d and theta naught. So yeah, I'm not sure why this can just lead to the total change of the argument. Yeah. Okay. So okay. Let's see. So okay. So let's focus on the residue. Okay. So while I'm waiting for the answer here, so let's go for the residue theorem. So shoot. So let's see the second part. So so let's see. So why the residue? Because the current residue theorem says that the integral that we want to calculate, the integral the 1 over 2 pi I integral over boundary of the parallelogram of zeta z dz, right, is equal to 1, right? It's equal to the one number of this boundary of the poles, the sum over all the poles of the one number times the residue, right, which is 1. Okay. So let's see. So why the residue of this zeta naught of this zeta z is equal to 1? Okay, so it seems that we will have F's Laurent series representation, right? So okay. So we know that this zeta z is equal to the sum Yeah, I think the question is that here the Laurent series expansion may not be equal to the same original zeta function, right? Let's see. So so we know that the zeta function is equal to what? The zeta function by definition is equal to okay, so zeta function by definition is equal to 1 over z plus summation omega not equal to 0 or in the lattice point of 1 over z minus omega plus 1 over omega plus z over omega squared. So okay, so the question is that what is the Laurent series expansion of this zeta at zeta now, right? Okay. Yeah, I think my thought is that zeta z is equal to 1 over z plus. So, you know. So we show that this zeta z is absolutely summable, right, at each point. So there's no problem of changing the order of the function. So what I do is that because we know that, so zeta now basically we know that it is a quote unquote singular point of this zeta z, right? So and the reason we know that is because here for each of the lattice point, right? Wait, why is a singular point? Okay, because of this, right? Because for each of the lattice point, there is this guy, 1 over z minus whatever the lattice point it is. This 1 over z function is give you the singularity of this lattice point, right? So gives the singularity of each gives the singularity of each lattice point. And then all the and because for each lattice point there is only one part from this infinite sum that corresponds to the singularity, and all the other part of the sum does not contribute to the singularity, right? Because if you pick any other summand, right, other than this, so if you fix a single point, let's say zeta naught, so there is one part from this infinite sum, right? So just to pick the part of the sum to be the part of the summand to be so that this omega is just zeta naught, right? So this only this term will correspond to a singular part, and all everything else does not is well defined, right? It's well defined at zeta naught, right? So and for that singular point, all else summand won't cause any extra singularity, right? I think this is the idea. Okay, so but how can we turn this into the expression? How can we turn this into the Lorentz series expansion? Because so basically the Lorentz series expansion, it has two parts, right? So one part is the usual Taylor series part, one part is the singular part, right? So the question is that how can we turn this idea into the Lorentz series expansion of this? So the question is that how can we turn this into the Lorentz series expansion? For this zeta z at zeta naught, right? Hold on. I think the idea might be that think the idea might be that idea. Yeah. So. So the idea might be that so yeah, so if you think of what does the right, so because our goal is to mainly to show the Laurent series expansion of this zeta z at zeta naught, because the only singular part is just come from the term that contains zeta naught, right? And all else does not contribute anything to the singular part of this this point, of the Laurent expansion at this point, right? So, so how can we utilize this idea, right? So, because contribute nothing to the singular part means that if we do the Taylor expansion of everything else, centered of anything right, of so basically no singular part means that the Laurent series. So if you say I have a holomorphic function and then it does not have a single part at a point, then that means that the Laurent series expansion is just the Taylor series expansion, right?